Hello and welcome to this lecture. We are going to start looking at the LDPC codes in the 5G standard. So far we have been looking at background on linear block codes, the basics, definition. So interestingly, that's all the background we need to define LDPC codes. We don't need to do anything more. So in this lecture we will define LDPC codes, and in particular we will also look at the definition of the LDPC codes in the 5G standard. It's easy enough to define. It is just a matrix definition, and we will do that in this lecture. Okay, so let's get started. So what is low density parity LDPC code? It is low density parity check code. Okay, so what is parity check? Any code like we saw as a parity check code, it has a parity check matrix. So we basically define this LDPC code through a parity check approach. We will specify the parity check matrix for this code. Okay, so that's why it's called parity check code. And what is low density? Low density means when you have a binary matrix. Remember, a parity check matrix is a binary matrix. It has zeros and ones. And when someone says it's low density, basically they mean it is sparse. So what is sparse? Sparse means there are many more zeros than ones. Okay, there are very few ones. Okay, the number of ones has to be considerably smaller, and anytime you have a parity check matrix with a lot of zeros and very few ones, you have a low density parity check code. So it's a very generic definition, and this looks like it's sort of weak. I mean, maybe you can take one or two ones here, there, and do it, but that's not how one needs to do it. We have to be a little bit more careful in specifying the exact sparse matrix. We will do that in this later on as we go along in this lecture, but for now the generic definition is that. Okay, low density parity check is a parity check matrix with very few ones. So usually you think of it as every column of the parity check matrix will have very few ones, and the whole matrix is made up like that. Okay, so here is so remember, the matrix is a k n minus k cross n matrix, right? So this is the H matrix. Now what is this notion of very few? Few in comparison to what? Few in comparison to the total number of entries in the matrix. Now n into n minus k is the total number of entries in the matrix. Okay, and the number of ones should be considerably lesser. So usually instead of having n into n minus k, you will have 3 times n, 4 times n, or 2 times n, some constant number into n, small number into n. Okay, so that's the idea behind this definition. So for instance, to give you typical numbers, if k is 1000, n is 2000, okay, you have 1000 by 2000 matrix. Okay, that has got like lots of entries, 2 into 10 power 6 number of entries. Now the number of ones is going to be 2000 into 3, say 6000. Okay, so that's it. So that's much smaller compared to the total number of entries. Such a matrix is called a low density parity check matrix, and that can define an LDPC code. Okay, so the definition goes back to Robert Gallagher. So he's the person who invented these codes back in the 60s. Okay, so it's a very old code in some sense. Okay, and at that time I think people did not really have the technology or realize the importance of these codes, and recently in the 90s these codes have been resurrected, and today so much research has been done and it is made into the 5G standard, for instance. Okay, so we won't look at the theory of LDPC codes and all that very deeply in this class. Like I said, our focus is on decoding and building decoders, and our focus is on the 5G codes. Okay, so we will simply accept the codes in the 5G standard as the LDPC codes we work with. Okay, so in this lecture I will mostly give you definitions for the codes in the 5G standard. Okay, but before that, there are a couple of concepts associated with LDPC codes which is very important. Okay, the first is that of a Tanner graph. Okay, so it turns out Tanner, back in once again the 80s, looked at these codes and came up with a nice pictorial notation which captures the essence of what happens in decoding and all that. It captures the code very well. Okay, so here is a parity check matrix. Okay, so you might look at this and say maybe it is not really low density, but this is just an example parity check matrix to illustrate the Tanner graph idea. Okay, so you have a parity check matrix here. It is a 3 cross 7 parity check matrix, and you can see it has ones and zeros, it has 1 here, 1 1 0 1. This is the parity check matrix of a code. Okay. Now, there is a Tanner graph associated with the parity check matrix. So, the Tanner graph is nothing but some sort of a graphical representation of the parity check matrix. How do we do this? Now, when you go from matrix to the Tanner graph, this is what you do. Okay. So, every column, okay, maybe I should write that out here. Okay. So, this first node here, the blue node on the left side represents column 1. Okay. So, this one. So, this column is represented by that node. The next one is column 2, so on. Okay. So, this is column 7. Okay. So, for every column we put a circle, okay, which is colored in blue in this picture, but in general let us say we put a circle for every column. Now, every row we put a square. This is row 2, this is row 3. Okay. And these are the two types of nodes in the Tanner graph. Okay. Graphs usually have nodes and edges. Nodes are connected by edges in the graph, and in this particular type of graph we have two types of nodes. One is what is called a bit node, it represents the columns in the parity check matrix. The other is what is called a check node, it represents the row in the parity check matrix. Okay. So, to distinguish between these two type of nodes, we draw circles for bit nodes and squares for check nodes. Okay. And how do we connect? Let me take row 2 as an example. Now, row 2 in the parity check matrix has connections to column 2, column 4, column 6 and column 7. Okay. So, that is why the row 2 node here is connected to column 2, column 4, column 6 and column 7. So, the edges correspond to ones in the parity check matrix. Okay. Wherever you have a 1 in the row, which column it has a 1, you connect that row to that column. Okay. So, it is a very easy and straightforward way to associate a graph with a binary matrix. This is quite standard in different areas, and in the error control coding area, this is called a Tanner graph after the person who came up with this notation. Okay. Now, this Tanner graph is very useful, particularly when you look at decoding for LDPC codes. Most decoders are described on the Tanner graph. A lot of properties of the code is studied on the Tanner graph, etc. For us, it won't play too crucial a role. We will worry too much more about the matrix as such, but it's good to know Tanner graphs because they show up a lot in the terminology for LDPC codes. And if you are interested in studying analysis of LDPC codes, you need to know about Tanner graphs. Okay. So, hopefully this is clear. Later on I will reinforce these ideas with some more examples, but this is the Tanner graph. So, with every parity check matrix, or in general any binary matrix, 0 1 matrix, you can associate a Tanner graph, right. You can draw some nodes for the columns, some nodes for the rows, and connect the rows and columns wherever there are ones. Okay. Now, what is special about the Tanner graph and what is the connection to the single parity check code? Okay. So, this is something that is very important. This will play a crucial role in all of our decoders. Now, if you look at a code word C, okay, with generated from a code with parity check matrix H, what do I know? I know H times C transpose equals 0. Okay. So, the vector 0, 3 zeros. Okay. So, any code word satisfies this condition, H times C transpose equals 0. So, now let us once again focus on the second row here, row 2, which corresponds to check node 2, okay, in this graph. Now, when you look at H times C transpose is 0, I have to multiply H with C on the right, C1, C2, C3, C4, C5, C6, C7. Okay. When I do this product, what will the second row tell me? The second row times this column will give me this equation. Do you agree? You take that second row and multiply with this column, I am going to get C2 plus C4 plus C5, C2 plus C4 plus C6 plus C7 equals 0. Okay. So, of course, this is all modulo 2 or XOR. Okay. So, in short, another way of viewing this is that instead of looking at the whole code word of length 7, if you look at only these 4 bits, what are the 4 bits I am going to look at? C2, C4, C6 and C7, only these 4 bits. Okay. What is the condition on those 4 bits imposed by the second row? It says that these 4 bits have to XOR to 0, which is, in other words, that these 4 bits C2, C4, C6 and C7 belong to the 4,3 SPC code, single parity check code, right. These 4 bits have to XOR to 0. Okay. So, each of these nodes here is a SPC code. Okay. So, in what sense is the SPC code defined? You go to this node, look at the bits that this connected to. Okay. So, this is what? This is C1, C4 and then C5, C7. Okay. So, what is this SPC code? C1, C4, C5, C7 are in the 4,3 SPC code enforced by this check node. Okay. So, every check node in the TANA graph enforces a single parity check code on the bits it is connected to. Okay. So, these kind of constraints are called local constraints. Okay. So, you have a code word which is global, you know, all the bits. Now, all the bits together satisfy every parity check in the constraint. Okay. Now, the number of parity checks could be many, right. So, if you think of a 1000 by 2000 matrix, you have 1000 parity checks. Enforcing all of them at the same time may not be a very easy thing to study. On the other hand, if you go and focus on one check node, one particular check node, and in particular, if this is a sparse matrix, then that check node is connected to very few bit nodes. Okay. And what these local constraints say is there are a few bits in the code word which satisfy the SPC constraint, single parity check constraint, and we know how to decode the single parity check constraint very well. Okay. So, this is one of the crucial ideas which is at the cornerstone of the success of the LDPC codes. Okay. So, to decode them, it is enough if you decode these SPC constraints, the single parity checks, cleverly in some order and combine them very smartly. Okay. So, how to do that is what we will see in the decoding section, but for now in this lecture we will focus on how the parity check matrices are defined in the 5G standard. Okay. So, hopefully this part is clear. This idea of associating a single parity check code with every parity check node is very crucial, and we will come again and again to this. Okay. So, another way of thinking about it is every row in the parity check matrix enforces one parity check constraint, right, on the positions of the ones. Okay. Wherever you have ones there, that row of the parity check matrix enforces a parity check constraint, and we will do decoding row by row, okay, and cleverly combine how we do the processing. And end up with very implementable decoders which also have very good performance. Okay. So, that is the crucial idea in some sense. Okay. So, let us also look at the TANA graph. I want to summarize some of the notations, and this I am sure you will see in many, if you read a book on LDPC codes, these terminologies will come again and again. Once again, I want to emphasize we are not doing a major theoretical study on LDPC codes here. We will be focused on implementation details, but nevertheless it is good to know some of these terms in case you come across them later on in your studies. Okay. So, the bit nodes in the TANA graph correspond to the columns, check nodes correspond to the rows, I mentioned this, edges correspond to ones. Now, this degree of a bit node is weight of the column. So, now what is weight of the column? This has weight 3, okay, number of ones. Weight of the columns is number of ones, and that is 3 here, that is 2 here, and if you go and look at the corresponding node here, it has 3 edges coming out of it, right. This has 2 edges coming out of it. So, the number of edges coming out of a node is called the degree of the node in the graph. So, degree of the bit node is the weight of the column. So, likewise the degree of the check node is the weight of the row. Okay. So, this one has weight 4 and the degree is 4. Okay. So, most of the analysis and design of LDPC codes focuses on the degrees. Okay. So, it turns out the degrees control the performance of the code. Okay. So, you have to do an analysis and study of it. And like I mentioned once again, we will not be doing analysis in this class. Nevertheless, these degrees and degree distributions are very crucial. Okay. So, that is a summary of what happens in the TANA graph. Okay. So, now we will jump into LDPC codes and standards. Okay. So, in the standards, it turns out 5G is not the first standard to incorporate LDPC codes. They have been there for a long time now, and many standards which maybe were not that popular. The most popular I would guess is the DVB S2 standard, which has an LDPC code. digital video broadcast standard, but now the 5G standard has made them much more prevalent than before. Okay, so it turns out the LDPC codes and standards are almost always protograph constructions. Okay, so this is not photograph in the sense of taking pictures. This is protograph. Okay, so what is a protograph? Protograph is sort of like an example graph which you repeat to make a bigger graph. Okay, so the way they would define protographs is as follows. So protograph construction is basically a way of constructing your parity check matrix. Remember, the parity check matrix is usually a big binary matrix, right? So 1000 by 10 2000 or some such matrix. How do you specify that? How do you specify where the ones are, right? So how do you specify the Tanner graph? So for that, the standards always use this protograph construction. There are a lot of theoretical reasons for why protograph constructions are very good, but let's just look at how they are defined and how they are specified. Okay, first thing they'll specify is the base graph or a base matrix. Okay, and base graph or base matrix. So this base graph is also called the protograph. Base matrix is the proto matrix, so to speak. Okay, and this base matrix is expanded or blown up, okay, to get the actual parity check matrix. Okay, so this expansion is by what is called right shift permutation matrices. I will show you precise examples in the next few slides, but you take a small base matrix and then you blow it up. Okay, replace each base matrix entry with a larger matrix to get the overall parity check matrix. So you can see this sort of controls complexity a lot. If you have a very large matrix, specifying where the ones are can take a lot of memory. Maybe not too much, but still it takes memory, and you want to minimize all of that. So to do that, you can do this base matrix which gets blown up. So you only need to specify the base matrix and how much you blow it up by. Okay, and this blowing up was also controlled by these right shift permutation matrices, so that you don't have to specify too much there. Okay, so the overall game is to optimize performance and complexity, and the theory is quite deep there. We won't go too much into it, and the only point is all standards have such codes. Okay, maybe sometimes the expansion is not by a permutation matrix, maybe it's by something else, but all standards have such codes. Okay, now specifically in the 5G standard, these are called NR LDPC codes. Okay, I think NR stands for new radio. Okay, so there are two base graphs that are defined, and there are several expansions. The expansion can be by as short as 2 by 2 to 384 by 384. Okay, so it's a very big expansion is also possible, and to achieve a lot of rates, they do something called shortening and puncturing. I won't talk too much about it in this lecture. Later on, I'll come back to it and mention it when dealing with these multiple rates and the so-called rate matching. So the rate matching is a pretty big deal in standards. People will talk about that a lot, so I'll briefly mention that. It's not very critical for us. Okay, so the most critical thing is there are two base graphs and there are several ways of expansion. Okay, so what is this base graph and expansion? Let's start by looking at a very simple small example where I will be able to show you the complete thing of what is going on, and then I'll point out to what happens in the standard. Okay, so here's an example. This is a base matrix. Okay, so an example of a base matrix. Okay, and the expansion factor is 5. Okay, so if the expansion factor is 5, the base matrix will have entries -1, 0, 1, 2, 3, 4. Okay, so these are the possible entries of the base matrix. So you can see that's what the entries are. There are a few -1s, few zeros, 1, 2, 3, and 4. Okay, here and there, just they are thrown in. Is that okay? So this is just an example base matrix. I'm not claiming that it is a particularly good base matrix. It's just an example. It may not be too bad actually. Okay, so this is an example of a base matrix that we are going to use to illustrate what happens in this expansion. Okay, so now the base matrix itself is not a parity check matrix. You can see clearly it's not binary. It has -1 entries and 3 and 4 and all. We can't do anything. So from the base matrix B, we will generate this expanded matrix. Okay, so, and this expanded matrix you can see is clearly a binary matrix, and it can be a parity check matrix for some code. Okay, so this is how the parity check matrix is actually specified. Okay, So, I have shown the expansion, I have illustrated it with these colored blocks. Of course, the colored blocks are just there for our convenience. The actual matrix has only zeros and ones. Okay. Now, how do we see this expansion? Let me show you what happens to each entry here. Okay. So, each entry in the base matrix gets replaced by a 5 cross 5 binary matrix. Is that okay? So, each entry replaced by a 5 cross 5 binary matrix. Okay. Now, if the entry is -1, you replace it with a 5 cross 5 all 0 binary matrix. Okay. That is what happens here. So, -1 got replaced by a 5 cross 5 all 0. Okay. Is that right? What about 0? The entry 0 gets replaced by 5 cross 5 identity matrix. Okay. What about the entry 1? The entry 1 gets replaced by a 5 cross 5 identity matrix shifted right by 1 position. Okay. So, this is the right shift permutation matrix I was talking about. It is a 5 cross 5 matrix, but you start with the identity and then you shift it right by 1 position. Of course, the shift is circular. So, the last entry will go off all the way to the right. Okay. You can see the shift happening here. Okay. So, it has been the identity matrix has been shifted right to obtain these ones here, right, and then the last one got shifted out to this side. Okay. You can see the shift by 1 to the right. Okay. What about 3? Any other value 3 is the same thing as what happened to 1. You take the identity matrix and then you shift it right by 3 positions, shift all the columns. When I say shift, I mean the shifting of the columns. Okay. So, you take the identity matrix and rotate shift the columns by 3 positions. Okay. So, you can see what has happened here. So, you will get 1 1 here and then that 1 1 1 here. Okay. So, and then you have a -1 which gets replaced by all 0 and then a +1 which gets replaced by identity matrix shifted right by 1 position. So, this is what happens to every entry in the base matrix. Okay. So, your original base matrix was 3 by 6. After you expand it, after you blow it up, you are going to get 15 by 30. Right, 6 into 5, 3 into 5, a 15 by 30 matrix. Okay. And you can see the 15 by 30 matrix is quite sparse, right. So, very few ones because we are using identity matrix and all 0 matrix, okay, and shifting etc. So, not too many ones in the overall final parity check matrix, and this is what happens in every row. In the second row also the same thing has been done, third row also same thing has been done. You can look at it and convince yourself that that is true. Okay. So, once again let me repeat, the base matrix will have entries, integer entries -1 up to the expansion factor. Expansion factor here is 5. In the 5G standard, the largest expansion factor is 384. Okay. So, the entries will go from -1 all the way till the expansion factor -1, -1 0 all the way till 4 if the expansion factor is 5. And what do you do when you expand or blow it up? Every entry in the protograph is replaced by the 5 by 5 identity matrix or the 5 by 5 all 0 matrix or the 5 by 5 identity matrix shifted right, rotate shifted right suitably as depending on the number that you have. Is that okay? So, this is the way in which you blow it up and you get a larger matrix from the smaller protograph or a base matrix. Okay. So, this is used in every standard that defines LDPC code in one way or the other. It is easy to specify. It also has very good properties, code properties and analysis is possible also to prove and design. You can design all this very well. Okay. So, what we are going to see in the next lecture is the actual base matrices in the 5G new radio standard. But let us close this lecture for now. We will stop with the example of the protograph matrix here. In the next lecture, we will see the actual base matrices in the 5G standard, how they are defined. It is just mostly specification, but I will quickly run through that and then I will point you to the actual base matrices themselves. Okay, so let's stop here in this lecture.